We have another example problem here. When a 60 Newton stone is attached to a spring scale and is submerged in water, the spring scale reads 40 newtons. What is the density of the stone? All right, so by saying a 60 Newton stone, this means mg of the stone. This is the weight of the actual stone itself. So if I were to hang this stone from a scale, not in water, the scale would read 60 newtons because the scale would be reading how hard it's pulling. And then the force of gravity on the stone itself would be the 60 newtons. So this is the weight of the actual stone. When we take this same stone, but we submerge it in water, the scale reads 40 newtons. The scale is still reading how hard it is pulling up on the stone, or how hard the stone's pulling down on it. The stone is still, so we can think of this is just the force of the scale. We have the 60 newtons downwards because of the weight of the actual stone. But because it's in water, there's also a buoyant force. The fact that it's displacing water means there will be a buoyant force. Now, according to Newton's second law, the stone's just hanging there, so the net force on this stone is 0. So we can say that the buoyant force and the force of the scale, both acting upwards, are counteracting or balancing out the force of gravity, the weight of the stone. Since we know the scale reading is 40, and we know the weight of the stone is 60, this tells us that the buoyant force is 20 newtons. Now, what this tells us ultimately, if we think about just the fundamental equation for buoyancy, that is equal to the density of the fluid times the volume of the object in the fluid. So the volume of the stone entirely in this case, because it is completely submerged, and then g. So that is our fundamental equation. So this tells us actually that the volume that is in, which is the volume of our stone overall, is equal to this force of buoyancy divided by the density of this fluid the stone is in times g. So 20 newtons. The problem tells us the stone is submerged in water. So the density of water from the table in the test notes, 1,000 kilograms per cubic meter. G is 9.8. So this gives us the volume of the stone. We don't know any individual dimensions because we don't know a shape, but that's okay. The volume of this stone, 0.002041 meters cubed. Now, we want the density of the stone. The density of our object. Oh, I'm just using subscriptive 0 to mean whatever object we're talking about. So the density of this stone will be the mass of this stone over the volume of this stone. Well, we've calculated the volume. We have that now. The mass of this stone we can get coming back to the weight of the stone being 60 newtons. The mass of the stone will be 60 newtons divided by 9.8 meters per second squared. So 6.122 kilograms. Write that better. Mass divided by the volume. The density of this stone turns out to be 3,000 kilograms per cubic meter. The reason it didn't sink to the bottom of the container is because it's hooked to the scale. So that attachment provides that upward force that works with the buoyant force to counteract the weight of the stone itself.